Hello, can you hear me? Great. I'm going to stand like this because we made the microphone very nice and tall. But welcome to DevSecCon London. It's our first in-person event in a very, very, very long time. So thank you all for coming out to see us. We also are live streaming, so you can all wave to everyone on the internet. But we will be live streaming today's event. So DevSecCon is very keen to make sure all our sessions are inclusive, regardless of where you are in the world, or if you've got jobs and families and couldn't find the building, like some people, I'm very sorry. So if you see any of our other events, we now have 21 chapters globally from every single continent except Antarctica. So if you see any of our other events come up and you're interested in what they're doing, whether they're in India, St. Paulo, France, most of those sessions will be live streamed, so you can keep up to date with all the content we have globally. I haven't introduced myself. I'm Sam. I work for Snyk, our lovely hosts, as a community manager. But Snyk actually powers all of DevSecCon. So most of my time I spend working with our chapter leaders to make these events happen. And so we're always looking for new chapter leaders and speakers and hosts. So please reach out to me. We also are going to be announcing next week our DevSecCon 24 event. So for those of you who don't know what that is, we live stream for 24 hours around the globe, starting in Australia and ending in the US. We follow the sun. We have live hosts, great speakers, just like the ones today. We'll be announcing it next week. So one, come along, but two, if you get inspired by these lovely speakers today or think they're speaking biggest load of bollocks and you want to prove them wrong, anything that inspires you, we do have an open call for papers. So please submit your sessions. You don't have to be a seasoned speaker. You can mention that in your abstract, and we'll even get community members to help you review things, put your talks together. You've all got amazing things to share. And whilst we love lovely humans like us speaking, we also want to hear from you. But that's enough from me. I'm actually going to hand over to our chapter leader, Andy Martha.
Yeah, brilliant. Thank you. So yeah, welcome to DevSecCon. Firstly, many thanks to Sam and the team from Snyk who've set all this up. Some of them you can't see right now, but a lot of work goes into this, audiovisual and just hosting us. Yeah, apologies on behalf of Andy. He's unfortunately unable to make it today because he's got other commitments. You should hold that against him. You know, get free beer next time. But yeah, not to fret. In his absence, we're graced by two of ControlPlane's best. We've got Rick, head of engineering, and James, security architect. And then no introduction needed for Liz, rock star of everything container. Yeah, she'd be in the Hall of Fame pretty much if there was. Brilliant. So the first talk this evening is from Liz. It's on eBPF Cloud Native Security. It's a powerful platform for the next generation of networking, observability, and security tools. And we'll explore together how it's being used for security in cloud native environments. So without further ado, please welcome Liz to the stage.
Amazingly, I think I've managed to get round to the microphone without disconnecting any of the cables behind the screen there, which is, I think, quite impressive. So I just need to start by sharing my screen. And okay, it has slightly messed me about, but let's hide these controls. All right. So I'm going to talk today about a technology called eBPF. Can I get a show of hands? How many of you have heard of eBPF? Excellent. Pretty much, maybe 3/4 of you. That's excellent. I will get the rest of you up to speed. Don't worry. I've written a few books in my time, 2 of which I have some copies of here. So this is my latest work, recently published, and this is also a fairly recent introduction to eBPF. I will give these away. This one goes to whoever asks the best question at the end. So I want questions, basically, and these to the runner-up, next best questions, all right? Okay, so eBPF, the acronym stands for Extended Berkeley Packet Filter. Put that out of your minds because it does so much more than filtering packets, kind of not really relevant anymore. What eBPF lets us do is program the kernel. So we can load custom programs into the kernel and change the way the kernel behaves dynamically. Make sure we're all on the same page about what I mean when I'm talking about the kernel. Most of the time, application developers are writing in user space, but whenever they want their applications to do anything that touches hardware, which includes writing to files, sending, receiving messages, writing things to the screen, all those things user space apps can't do directly. They have to ask for assistance from the kernel. The kernel's also involved in managing multiple processes that are running simultaneously. So when we come to thinking about security, a lot of those events are really relevant, right? We usually want to know about things like file access, processes starting and stopping, networking, and so on. So hold that thought. With eBPF, we can attach programs to basically any event that's happening across the system. We can attach to any kernel function. We can actually attach to pretty much any line of code in the kernel. We can attach to events like network packets reaching certain points in the networking stack. We can attach to trace points, and whatever the event is that we attach our program to, whenever that event happens, it's going to trigger our program to run. So the kind of hello world, and hopefully if I can find the right screen, I've got a little example hello world, but let's make this say hello DevSecCon. And if I run this, this program, this is the eBPF program here. And all it does is it's going to write a line of trace saying hello. There's also some code here that loads the program into the kernel and attaches it to the execve system call. This is what's used to run a new program. So whenever I run a new binary program, execve is going to get called. So I'm going to run this program. It's more than one. And hopefully, if I run some programs, you can see every time something happens, it's triggering my hello program to run. And I have changed this. This is coming from the kernel trace file, this tracing output. Would I like to join audio to speak? I don't think I would. No, I think that would mess me about. Okay. Right. No, where have my slides gone? There they are. Okay. So this is basically the hello world you just saw. In that tracing output, not only did we get the trace message, we also get information about the process that triggered that event. And this is generally true that when we have an event, the eBPF program gets passed some contextual information about what that event was. So here's the network packet that arrived, or this is information about the process that was running that triggered a certain system call. So this can be the basis of lots of tracing tools that you can load dynamically into a system. So, for example, if you want to collect some kind of metrics about different events, you'd have some tracing tool that loads an eBPF program into the kernel. And it also uses what's called an eBPF map, which is basically a data structure that can be accessed from eBPF programs and also from user space in an efficient way. We attach the program to an event, and then whenever that event happens, it generates metrics, stores those metrics into the map, and then our user space tool can collect those metrics kind of asynchronously. So we don't have to wait for a transition between kernel and user space to generate that metrics event. It can happen asynchronously. There are tons of tools that have existed for quite a long time that instrument all kinds of aspects of the system. First time I saw this diagram, I have to admit I was pretty scared. It's pretty overwhelming. What is all this stuff? Don't worry about all the details. The point is you can find existing tools that instrument all these different aspects of the system, whether it's looking at file system metrics or memory being used or out of memory instance. All these things can be traced by eBPF. And there's a set of tools in this project called Isovalent BCC that has this very wide range of command line tools that are pretty interesting. One of them, I'll show an example, is OpenSnoop. So OpenSnoop shows us whenever a process opens a file. So again, if I can find the right window, I think it's on here. I also think it's called OpenSnoop BFCC on the system, I think. Yeah, that's looking encouraging. So there's all stuff happening on this virtual machine. It's reporting those files and in some cases pseudo files being opened, and hopefully if I file, we should see, yeah, we see not only the access to my file, but also cat. Ooh, when I ran cat, it also opened a bunch of shared library files as well. Now, importantly, I didn't have to change anything about my cat application, for example. I just instrumented the kernel and it was able to see that application and see every application opening every file on that system. And that's really the basis of what makes eBPF so powerful, that it has this visibility over the whole machine. So let's think about what that means in a containerized environment like Kubernetes. We're typically running our applications in containers inside pods, and they're running in user space. However many of those pods there are, however many containers there is only one kernel per virtual machine or bare metal machine. So all of our pods are sharing that same kernel. They're using the same kernel's resources whenever they want to do anything like send or receive network messages, read and write to files. Even when Kubernetes is creating containers, it's starting processes, and that's using the services of that kernel. So if we instrument that one kernel with eBPF programs, we can see everything that's happening on that whole machine. All of the Kubernetes pods on that given node will be visible to eBPF tooling running on that machine. And we don't have to change anything about those applications or the way they're configured. They're still going to be visible. One thing we do want is information about the Kubernetes context. It's one thing to say a certain process is running a certain application and maybe it opened a given file. But what we really want is this kind of Kubernetes context where we know what node and what pod and what namespace and so on is running. This tool called Inspector Gadget is an example. It's just recently joined the sandbox in the CNCF. And again, I hope I'm going to be able to show you that one working. So let's see. Yeah. So if I trace, hopefully, yeah, there's quite a lot happening on this little tiny cluster. And you can see information about the node and the namespace and the pod and all the rest. And that's really essential, because if you want to debug a problem, or you want to, if you're interested in file open events for security purposes, you're really going to want to know which pods are responsible. Another example of an observability tool in the CNCF is Pixie. And I'm really showing this because I think it's a good example of how we can aggregate information from across multiple nodes and show that information in visual form. Pixie actually supports tons and tons of different eBPF metric collections, a bit like that diagram I showed you with lots of different tools. a similar range of things are available in Pixie. This is an example of collecting a flame graph showing CPU usage across the entire cluster. It aggregates that information collected on all the nodes. Pretty cool. It could be very useful if you're trying to understand where your resources are going cluster-wide. Another example of observability would be network observability. I work for Isovalent, which is the company that originally created Cilium. Cilium is a pretty well-known networking solution in Kubernetes and beyond. Actually, let's do another show of hands. Is anybody here using Cilium? Few hands. Okay, hopefully more of you will be in the future. Cilium includes an observability component called Hubble. Hubble uses eBPF to collect information about all of the network packets that are flowing through the system, and it can use that to collect together, or aggregating that information together, we can build up service maps so we can see how different services are communicating with each other. We can also collect Prometheus metrics and understand about performance, for example, the latency graph that I'm showing here. So I've shown you a few tools that are used for observability in eBPF, but we're all here to think about security. So let's just think about the term security observability for a moment. The difference between regular observability and security observability is having a policy. So rather than saying, I'm interested in all of the file open events possible, I might be only interested in a certain set of sensitive files. So comparing behavior against a policy can tell us whether or not something is malicious or potentially malicious. Somebody accesses the etc. password file, that's probably something that we want to be aware of from a security perspective. And we'd normally, when we find behavior that's outside of a policy, we probably want to send logs to some kind of SIM. Maybe we want to generate alerts so that somebody can take a look and see what it is that's causing this problem. And we want to have that contextual information about what process, in what pod, in what namespace, on what node, and so on, so that we can really understand where this potentially malicious behavior is coming from. And eBPF is really great for doing that, collecting that information. And you've seen that we can collect events and match them up against Kubernetes identities. As I mentioned pretty much at the start of this talk, the kind of things that happen in the kernel are pretty typically the things that we're interested about from a security perspective, like accessing memory unexpectedly, unexpected network traffic, or file access, or privilege escalation. One way that we can detect, or one way that quite a lot of security tools use eBPF, is to monitor system calls. So we know that the user space application is going to make system calls to do all these things. So if we can observe those system calls, perhaps we can use that information to detect security relevant events. There is a problem with using the syscall interface, and that is when you make a system call, you're passing some arguments to that system call from user space into the kernel. And those parameters have to be copied into kernel memory space. There is a small window of opportunity that was discussed at length in DevSecCon, I think in 2021, DevSecCon 29, and then explored in more detail at the eBPF Day in 2021, talking about how attackers can potentially exploit this window to change those parameters. So, for example, if you were opening a file, an attacker could change the path of that file, change the file name in between making the system call, so what gets reported, and the file that actually gets opened. And that's not great from a security tool perspective. In fact, the kernel there's some kernel documentation that talks about this interface and says, do not build security tools on this interface because it's not intended to be safe. So while there are lots of useful things you can do by observing system calls, it's not really safe for thorough security tooling. We need to make the check later. We need to make those checks after the arguments have been copied into the kernel memory. There's a great interface for doing this, and you may well have come across it one way or another before. How many people here have used SE Linux? Yeah, about half people here. So SE Linux is an example of a security module that uses this Linux security module API, which is a stable interface inside the kernel that it sort of hooks into these security relevant events like opening files. And SE Linux allows you to put policies sort of on that interface, so you can see whether or not, or you can reject calls if they're not compatible with the policy. We can use that same LSM interface for eBPF programs. We can hook programs into that same interface. And that's kind of more, well, it gives us the opportunity to dynamically change policies, to be a bit more dynamic about how those policies work. If anybody's ever tried configuring SE Linux or AppArmor, they're not the most easy to use tools. With eBPF, we can build something that's a bit more customizable. We can have a nice user interface and make easier to use security tools. And we have the benefit that this is going to protect pre-existing processes. We can load an eBPF program and it will act on all of the processes, whether they were running before or not. I don't have this demo running today, but this would be an example of a kind of LSM hello world, if you like. The sort of hooking into, in this example, it's changing the permissions on a file, and you get not just the fact that, you know, it's not just hello world, but here you get the file name. And that is the file name from the perspective of the kernel. You can see this path, D entry, DI name. This is the kernel's data structure representing that file. So you know you're looking at the right thing that the kernel is potentially going to act on. There is one problem with this LSM interface, and it's that it's relatively new. You need a 5.7 version of the kernel, and there aren't that many Linux distributions that people are using in production today that are using such a modern kernel. In fact, this is the reason why eBPF is becoming a lot more popular, because people are starting to use versions of the kernel that have more and more eBPF capabilities within them, so we can start taking advantage of them for things like security tooling. The other thing that the LSM interface doesn't have by default is any knowledge of Kubernetes. The kernel doesn't know or care about Kubernetes. It relies on programs to make that connection between various kernel constructs and the Kubernetes containers and pods and namespaces. A little aside about how stable the Linux kernel is. So I mentioned that, let's go back here, that the LSM is a stable interface. That means it's not going to change from one kernel version to the next. It's kind of guaranteed to stay compatible. There are plenty of places in the, I don't know, 30 million lines of code in the kernel that don't change very much and haven't changed for a long time. They're not guaranteed not to change. They're not officially stable interfaces. But if you're a kernel developer, I'm not, a lot of my colleagues are, they know that certain parts of the kernel haven't changed for a long time and are very unlikely to change in any significant way going forward. They would know if there were plans for them to change. So potentially there are other places in the kernel that we can hook into that have existed for a long time and will continue to exist in the future, even though they're not part of that stable LSM space. And that is what the Tetragon project, which is a sub-project within Cilium, uses to provide security information. So we don't actually hook into the LSM hooks, we hook into kernel functions that we know to be sufficiently stable that you can use them in kernels going back to 4 dot whatever. And also in Cilium we have the knowledge about how to match kernel structures to Kubernetes identities, because we've been doing that in Cilium for a long time. So we can provide both of these kind of parts together and put it into this tool called Tetragon. The Tetragonisca angostula B is I think it's a prolific producer of honey, and it's not aggressive and it's not harmful to humans, which is, as you probably noticed, the B is the symbol of eBPF, so Tetragon is a type of B. So Tetragon has policies, talks about the need for policies that that tell Tetragon what kind of events we should be interested in. And it gives us some filtering that we can do in kernel. So this example is going to follow a file descriptor. So when we open a file, we would follow that file, but it's only interested in files that are in the etc. directory. Being able to filter these events in kernel rather than sending all of them to user space event makes a huge difference to performance. And the kind of output that we get would show us the events, relate them to the Kubernetes pods and namespaces and so on, and show us events that are outside of policy. For example, here, writing, I think actually here it's probably reading some, no, it was writing, it says right there, showing us exactly what's been happening. So I have an example of this that I can show. So hopefully there's something slightly weird awry gone with my screen formatting. So you can see lots of events being reported here by Tetragon, showing us file accesses, showing us actually, I think this example, showing us the parameters to different commands and so on. I'm just putting these into the screen. You can imagine sending all of these kind of interesting security events to a SIM and then being able to explore them and understand what's happened later. Okay. Imagine also, I don't unfortunately have this running as a demo, but imagine being able to map those events to the process tree. So we can say, not just here is a particular executable in this particular pod, in this namespace on this node, but also what was the ancestry tree for that process? In other words, what container started it, what commands were running, what caused the event that we're interested in. For example, here, maybe we think that this not reverse shell.com network access looks kind of suspicious, and we want to be able to trace back to find out when it happened, which pod's been compromised, what it is, what executable it is that looks as though it's been compromised. Super useful for diagnosing, getting forensics on security events. Also, kind of, let's say beta, maybe not even beta level capability that we have in Tetragon is the ability to prevent these events from completing. we already have eBPF being used to provide preventative security. We don't talk about network policy being preventative security, but when we have network policies, we expect to drop packets, and in Cilium, we drop those packets using eBPF programs. For runtime security events, I think as an industry, we tend to be a bit more conservative, and we tend to say, you know what, I'm a bit scared about preventing it. I will let it happen, and then I will audit it later, and I will have the forensic later. I think that's mostly because network attacks happen, you know, all the time, millions of them. We would never get anything done if we were trying to diagnose network attacks after the event all the time. We just have firewalls. We're used to this idea of dropping packets. But what if we had a bit more preventative security for runtime events? Normally, the problem is that most security tools assess whether something is in or out of policy in user space. So even if we detect the event in the kernel, sends it to user space says, yeah, that looks really suspicious. I don't like the look of that. Maybe it sends a kill signal to that process, but it could be too late. Information could have already been exfiltrated, for example. With Tetragon, we have this ability to send a kill signal synchronously from within the kernel. So because we're filtering those events in the kernel, we say, yeah, that looks suspicious. I do not want anybody opening, writing to the etc password file, let's say. If I see that, I'm going to kill that process. And because it's killed synchronously within the kind of life of the system call that's making that write request, the write never gets to complete, and we can kill that process before the write actually gets to take place. So eBPF security allows us to instrument all of our applications dynamically. We don't have to change our applications. We're going to see everything that's happening on the node that's instrumented without having to make any changes at all to the apps or the way they're configured. We can build tools that are Kubernetes aware, and this kind of option that's coming for better runtime enforcement that we can control and run from within the kernel. How many people think they want to write eBPF code themselves here? Okay, a few hands are up. Don't worry if you're not thinking you want to write eBPF code yourself. That is totally appropriate for most people. I mean, eBPF coding is pretty quickly becomes kernel programming. So for most of us, it will make sense to use programs that people who are very familiar with the kernel have already written. For you, this book I recommend because it gives you a better, like, high-level view of eBPF. If you are interested in a bit more kind of getting into the details of how it works, and certainly for me, I wanted to understand how it works at a programming level so that I could, talk about it, understand it properly. And that's why I wrote that book. And hopefully that would get you off the ground if you want to learn how to write eBPF code. Either way, there's some labs on isovalent.com that will show you. There's some eBPF specific labs. There are also some Cilium and Tetragon labs, so you can explore how those work. You can download electronic copies of both of these books, plus also a security observability book written by some of my colleagues from isovalent.com. And yeah, I have one copy of this for the best question and 5 copies of this for the next best question. So I hope there are going to be 6 questions. That's it. Round of applause, please. Let's start at the front. I will repeat the question for the benefit of YouTube. So the question is it possible to use eBPF on managed Kubernetes? I think, did you say EKS? Yeah. So, and that is a good question. So it depends whether or not you have access to the nodes and or have ability to run privileged pods. So if you're deploying, say, for example, Tetragon, you're going to need to deploy a daemon set that will require privileges. Not all Kubernetes services will let you do that, some will. Some of those tools like the CLI tools, like OpenSnoop, if you can't SSH into the node, you can't run those tools. In many cases, the cloud providers are really interested in eBPF. I mean, all of the major cloud providers are now using Cilium in one form or another. So for example, Google's GKE DataPlane v2 is based on Cilium. AWS use Cilium by default in EKS anywhere. Azure just announced that they're building Azure CNI powered by Cilium. I hope I got that name approximately right. So there's a lot of appetite in the cloud providers to use eBPF based tooling. I also saw a talk, and I can't remember what the name of the project is, but AWS have a security tool that's using eBPF information. Yeah. All right. There was a question there. Okay. Yeah. Yeah, good questions. Okay, so the first part of the question is, what's to stop an attacker from killing the program that's using eBPF to monitor security events? And the second part of the question is, can I use eBPF to affect another eBPF program? So the first part is, can your attacker may, I mean, it depends on the level of privileges that they've managed to get, right? So you need privileges, kind of, there's cap BPF and either cap net admin or cap sysadmin, depending on the type of program. So you need those capabilities to affect the eBPF programs that are running in the kernel. You should treat those like root, if not root++, because it's, you know, if anybody who can load an eBPF program into the kernel can, you know, that they have access to everything. So if an attacker has not got those privileges, but like you said, there's a user space process that's running that is reading that information out of the map. So let's say they've got the ability to kill that process. Yeah, that doesn't remove or doesn't necessarily remove the eBPF program in the kernel. There's some niceties to that, but assuming the tool is well written, it's going to stay loaded into the kernel. So you'd still be collecting the events. You'd have a buffer of time for your user space program to restart and then start sending events to your SIM or whatever it is you're using. The second question is, can you use eBPF to modify eBPF? Yes, there are some, I mean, there's some great examples like using eBPF to see what eBPF programs are loaded. You can, there's also some, let's say, conflicts where you, in certain places, you can't load more than one eBPF program on the same event, but it sort of depends on the context. I think the answer is, if you're going to use eBPF tooling, you kind of want to be, you want it to be there first, you know, and you want to but if you own that machine, you can load the eBPF programs yourself. You can use eBPF to monitor whether anybody else tries to load any eBPF programs. Yeah. Sam's put her hand up. Am I? Okay. I'm not going to be able to send the book through YouTube, but we'll figure it out. Oh, okay, great. Okay. 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 Oh, amazing. Yeah, so last year, about a year ago, we announced Cilium Service Mesh. So Cilium already does a whole load of the capabilities that you associate with Service Mesh. It does load balancing, it does observability. I showed you some observability. It does various forms of security, and all of those things are characteristics to the Service Mesh. So there wasn't a huge amount more that we needed to do. It also does layer 7 parsing, so we can do layer 7 network policy enforcement. So it wasn't a huge step to go from there to a service mesh. We currently support Kubernetes ingress and gateway API as of the most recent release of Cilium, which is 1.13. So yes, we do support service mesh. There is one piece of the puzzle that is arguably missing, but is, well, essentially now falling into place. A lot of people use service mesh to have mutual TLS between applications. We already had the ability to encrypt traffic using node-to-node transparent encryption. We now have the ability in 1.13 to use identities like spiffy identities to do application level negotiation of the identities for encryption. There's a bit more work to do on the control plane side of that. How do you get those identities and associate them with those connections? But the fundamentals are there. So I think the question was, can we use it to service mesh? And the answer is yes, and increasingly more so with newer releases of Cilium. I'll start on my left and work along. Yeah. Okay. So the first part of the question was, are there any eBPF-based honeypots? It rings the bell that there is, but I can't remember what it is, so I'm going to just pass on that question, I'm afraid. The second part of the question is about supply chain security, and I'm going to paraphrase your question as, what happens if your eBPF program is somehow malicious? You've used the wrong thing. So very important that you get your eBPF programs from a trusted source. And you could, for example, be use, if it's installed through a container image, then making sure that the supply chain security for that container image is that it's signed and so on. There is also work afoot to have the kernel check, essentially to have signed eBPF programs, so that as you load it into the kernel, it could be verified. For reasons that we can talk about after questions, because it's kind of really cool but quite complicated. For reasons, it's really quite hard to you can't just sign an eBPF program. Um, and, but there is work afoot to address that and yeah, have signed eBPF programs. Okay. Okay, so the first part of that question is what are the guardrails? That's a really interesting one. I will answer that. The second part is does the time spent while you're in the kernel context of the running that eBPF program, does it kind of count against the that process's use of CPU? I don't know the answer, but I do know that it will be whatever is true of when you make kernel requests. I'm sure it will be accounted for in the same way, but I don't know whether that counts against user space or not. So not a great answer, but it'll be one or the other. So the guardrails question is really interesting. Something I didn't talk about is how when you load an eBPF program into the kernel, it goes through a process called verification, which explores all the possible paths through the eBPF program to make sure that it is safe to run. So that it definitely runs to completion, that it's not going to dereference a null pointer anywhere, that the memory access is safe, and that it only makes there's a limited set of function calls that different types of eBPF program are allowed to make depending on their context. So the verification process is what's really providing those guardrails and guarantees that it's safe to run. Doesn't guarantee that it doesn't do anything malicious, but guarantees it's not going to crash it out. I'm working along the row at the back. Okay, so this is about how eBPF programs can attach to different events. Some of those events include co-probes in kernel space and U-probes in user space. And I've forgotten where it goes from there. It was, oh yeah, whether or not, like how does it attach to those U-probes and whether or not that's sensitive. I mean, it's the same, it's using the same mechanism as like tracing uses to attach to U-probes anyway. Is it sensitive? Well, anything that's, you've got to trust your kernel and you need to trust anything that's running in the kernel, including anything that's eBPF. So if you have an eBPF program and you don't want it to attach to certain user-based events, then don't run that eBPF program. I don't think there's any way around that. Okay, you're saying can the U-probe sort of affect the behavior of that eBPF program? I guess it would be possible. I mean, you'd have to be running an eBPF program that does something, I don't know, interesting, not just monitoring that U-probe event. And then, I mean, I suppose at a pathological level, you could have a U-probe, you could have an eBPF program that attaches to a U-probe that kills processes. I mean, yeah. I think I'm still going to lean on be careful what eBPF programs you run. Back to the front. When not to use eBPF. I mean, I might be biased. There might be scenarios where you can't, because maybe you don't have access to the underlying node. You don't necessarily have the privileges to run eBPF. And also, I think there are lots of things that you could theoretically do or build with eBPF, but depending on, not you individually, but depending on your skills as a abstract person, you might find it easier to do something in user space. If you were doing something that's not performance critical and you know how to do it in some kind of user space language, then there's no, I often think that, the best tool is the tool that you are familiar with, and that comes for programming as well. Like I say, eBPF can pretty quickly be kernel programming. So, you kind of need a reason why you want to do it in eBPF first. Aha! So the question is, will eBPF be endgame for sidecar containers? I have done a talk a couple of times on exactly that topic. I think it gives us a much better model for most infrastructure tooling. So sidecar containers, you have to inject that container into your pods. It doesn't come for free. It has to be injected. That means two things. First of all, it has to be injected without, no problems can interfere with that process. And if anything goes wrong with that process, the pod is not instrumented. The second thing is that if you have tools that require some kind of resources, the proxy that you use for service mesh being a great example, where every proxy needs a copy of routing information. So if you've got lots of pods with lots of copies of that routing information, it's potentially not very efficient. If we can move that out so we only have one instance necessary, because we can use the kernel to interface to that proxy, then it's more resource efficient. And we know that everything is instrumented on that node if we've instrumented the kernel. My only caveat to will it be the death of sidecar containers is kind of the answer to the previous question, which is if you don't have the skills or don't have the time to write a eBPF version of something, then use the sidecar container approach that exists. The thing that exists is better than the thing that's imaginary. And also, if you don't have access to the underlying node, you may have to use sidecar containers. Oh, actually, no, let's go. Yeah. Yeah. Yeah, okay. So the question's really comparing sort of SE Linux and why eBPF-based tools could be better. I wouldn't say that eBPF yet has more adoption than SE Linux. I think SE Linux is pretty widely used. But I do think an awful lot of people rely on some pretty default SE Linux. They never change the config, hope it's all right. And I'm sure it is used in some cloud native environments, but I think it's less used in cloud native environments than it was in the VM world and bare metal world. The advantage you get with eBPF is that you can customize everything about this. So with SE Linux, you've got, however they configure, the configuration files are in a certain format. That's how you configure it. You could write eBPF programs that, there is no limit to what you could build to configure in some much more usable way. I don't necessarily know that all of the tools exist in all of the forms that people will want, but there's just so much, there's infinite flexibility building on eBPF as a platform. So things like the way tetragons kind of, using little pretty icons to show you what's happening. That's just a trivial example of something that is pretty easy to do, because you have the flexibility, because you're building something from scratch. Yeah. So the questions about whether there are any guidelines about writing safe eBPF programs. The verifier kind of acts as those guidelines, and things like when you're inside an eBPF program, you know how when I did tracing here, and there's like a BPF helper function here that generates this trace line. I can't just call any old kernel function from here. I have to call BPF helper functions. This is an example of a helper function. The set of helper functions you can call depend on the type of eBPF program and where it's attached. And that provides a lot of safety around what memory you can access, which is kind of, the root of all protection. The set of helper functions continues to grow to allow people to build more and more interesting functionality in eBPF. But I would say that the maintainers of eBPF are very careful about what they're allowing people to do from the context of eBPF, with security very much in mind. Obviously, code is code, and not that there won't ever be vulnerability, but they're certainly very aware of the consequences of what you yeah. Thank you very much for an amazing set of questions. I'm going to have to make some decisions here about who's getting some books. All right. Okay. I don't want to shut my screen down. Should I shut this? There's something else doing it. Can I leave this? I can leave this okay, can I?
Hello, Internet.
Test 1 2 1 2. What about from here? Is it okay from here?
Intermediate between. I'm first, then Rick. So Rick's probably a bit taller than slightly.
Brilliant. Welcome back, everyone. Again, thank you to Liz for the talk. It was amazing. Really good questions. If you can regurgitate more questions at the end of this, it'd be appreciated, or maybe not. Bring it down a level. Yeah, Rick will appreciate it. So we've got a talk from Rick and James from ControlPlane in place of Andy. Again, apologies on Andy's behalf. They're going to do a talk on what can go wrong when you trust nobody. So it's looking at zero trust and the philosophies around that and how. So I'll hand over to James.
Thank you very much, Ian. As Ian says, we are going to be talking about what can go wrong when you trust nobody, threat modeling, zero trust. This is us. I am James. I am a security architect at ControlPlane. When I am not working, I am usually being walked by my dog, as you can see there. And I also make music under the moniker of Mons Electric. I do not actually play bass, but I can never resist a good opportunity to get a very niche Spinal Tap joke into a presentation. We've got Rick, who will be doing the second half of today's talk. Rick is head of engineering here at ControlPlane. He wouldn't put a comedic second bit to the intro. Okay, so about ControlPlane. So we are a cloud native consultancy. We specialize in cloud, Kubernetes, and containers. We specialize in consulting for highly regulated industries. And we're around 50 people, but growing, spread all across the world. So what is today's talk going to look like? We're roughly going to split this into two parts. So in the first part, we're going to talk about threat modeling and how it pertains to zero trust. In the second half, once we've built up a secure architecture through the process of threat modeling, Rick is going to give a demo of the system, which we build up from scratch during the talk. It's worth saying the first thing we have to do when we threat model is to scope the threat model. Zero trust is a huge topic. We are going to focus here on zero trust for workloads. So workload to workload interactions rather than user interactions. We're not going to address zero trust in the supply chain, which would be probably a conference on its own rather than a talk. So first of all, what is threat modeling? A very high level overview. You can see the Bible of threat modeling by Adam Shostak on the right of this slide. Threat modeling is basically identifying threats and vulnerabilities to your systems, devising mitigations for these threats, prioritizing risks which may remain following the implementation of mitigating controls, and then escalating these risks up the appropriate security governance chain. So why threat model? Well, we do it every day. Every time you cross a road, you perform a threat model in your head. So why should we treat our systems any differently? The benefits of threat modeling include identifying security flaws or potential security flaws as early as possible so that we can rectify them. This can save money and time. It can focus security requirements, and we can identify complex risks which may otherwise be left unattended. Everyone can and should threat model. It's not just for security teams. The best people to threat model are the people who understand the features and software that is being developed. So threat modeling absolutely is for everyone. That's a really important message of today. So the threat modeling process is iterative. We can start, hopefully, before we start building a system. However, it's like the old ancient proverb, the second best time is now. So the first question we have to ask is, what are we building, or what have we built? And this entails understanding the data that we're processing, our adversaries, and our architecture. So we want to be drawing architecture diagrams, we want to be drawing data flow diagrams, capturing stuff in information flow matrices, anything which can prompt robust discussion among the people who are building the system. The next bit is the fun bit. What can go wrong? So once we know what we have built, we use techniques, and we'll go through some of these today, such as stride and attack trees, to tear apart our system, think like an attacker, and answer the question, what can possibly go wrong? Next, we have to say, what will we do about it? So we have to devise our controls, like I said, which mitigate our threats. And finally, like I said, this is an iterative process. We've always got to be asking the questions, did we do a good job? Are the controls that we implemented working? We can learn about this through automated testing. We should be testing the control effectiveness rather than the specific implementation of the control. So let's try to make sense of zero trust. I think zero trust is yes, question. Sure. Fine. That's a really good question. So for everyone on the internet, the question was the questions that we raised. How do we put this into software, or is this just for discussion? So this is kind of the way we brainstorm. So what we would usually do is run a workshop where you get all the right people in the room to talk about the specific questions. So when you're talking about what can go wrong, you want to get your software developers together and start thinking, well, what can go wrong in this particular method, or this when this function is called here. So you just need to get the right people in the room at the right time. You of course have to document that, and we'll show some ways of documenting it later in this talk. So what we're going to do in this talk is build up a system, threat model it in real time, and Rick's going to show it working at the end of the talk, when we'll actually build some custom controls, because sometimes the default controls may not be good enough. So that's the rough outline of what we're doing here. But zero trust. So we spoke a bit about scope and how we're not talking about software supply chain zero trust, or zero trust for users interacting with workloads. We're focusing on machine interactions. However, zero trust is thrown around as a term a lot, and it's become a bit of a buzzword. I'd like to show that we can actually make good sense of what this term means by starting with a very, very basic threat level. So we're going to start with something sky high level, which is just a user somehow interacting with a workload, two workloads communicating. Workloads may be persisting data, they may be interacting with previously persisted data, and workloads are talking to cloud provider APIs. The key to deriving the zero trust principles from this diagram is that we are not specifying anything about where the workloads are running. So these could be on-prem, this workload 1 could be running in AWS, workload 2 in Azure, the cloud provider API could be anything. We're not specifying anything, and we are drawing trust boundaries absolutely everywhere. I realize that's a bit of a circular definition, defining zero trust by drawing something called a trust boundary, but it should become clear later on what we actually mean by this. A good example is 10 years ago, it used to be common for people to say, well, workload 1 and workload 2 are within our restricted network, therefore we know traffic from one is trusted. Maybe there's some firewall rules saying that this subnet can talk to this subnet. This doesn't really work in the modern cloud native world, because we've got ephemeral workloads. Most things are running in containers. We have to find a new way of doing things. And what this is going to rely on is getting a strong form of workload identity, which we can base policy decisions on. So what we're going to do, very high level, we're going to threat model this diagram. We're going to use stride to do this. So stride is a nice mnemonic just to help us brainstorm threats. So S is for spoofing, T for tampering, R for repudiation, I for information disclosure, D for denial of service, and E for escalation of privilege. So what we're going to do is just go through each of these one by one, not going into too much detail on this. Spoofing, we can either spoof a user or a workload. In the controls section for the user threat, we've got standard authentication best practices, IDP controls such as MFA. When it comes to workload, this is where we need this cryptographically strong workload identity. So bear that concept in mind, because we're going to be talking about that a lot. Also, if we could have all of our workloads talking over MTLS, that would be good, because then we're doing both verification of the client and the server. Going into tampering, altering information in transit is a risk, also protected by the encryption provided by implementing MTLS. We could tamper with stored data, and here we're back to strict authorization policies everywhere. Repudiation, so can I, as a bad entity, do something bad and claim Bart Simpson style, I didn't do it? And here we again come back to this idea of cryptographically strong identity, but we also want to tie things back into audit logs so we can do forensic analysis on anything which may have gone wrong. Information disclosure, can I exfiltrate data? Again, egress control, policy as version code. Policies will always have a root in business logic. So do we understand who owns this policy? Can we understand the version control? How do I make a change to this policy as someone who wants to see something work differently in our architecture? Finally, denial of service. So can I prevent workloads from communicating? Could I subvert this mysterious, for now, workload identity mechanism to stop workloads from getting their identities? Therefore, we have to have a highly available mechanism that will do this. We won't go into too much detail in this today, but this will be a key concern of running this stuff in production. And finally, I said finally before, really finally, escalation of privilege. Like I said, we're not treating the software supply chain risks in this talk. So there's always going to be the chance we can start from our threat model with the point at we've got a compromised workload running in our Kubernetes cluster, for example. So the question then is, could this workload pivot, and how do we prevent this? Again, least privileged authorization policies is the way forward. So we have some high-level architectural principles. The next thing now is to build a real architecture. Disclaimer up front, we're not saying that this is the architecture or anything. This is an example architecture we've built to illustrate the most important principles we're talking about. So what do we need? This cryptographically strong workload identity I keep going on about. We're going to use a technology called Spire. Now, Spire is a production-ready implementation of the SPIFFE workload identity framework. And I'll show how it works on a later slide. For now, all we have to know is that workloads can get identity documents issued by a Spire server, and then they can use these workload identity documents to prove who they are. So now we have a workload identity. We can ask, can we authenticate to cloud services using this Spire issued identity? And the answer is yes. We can set up a cloud provider identity OIDC provider. We can get that OIDC provider to trust our Spire server, so to trust the signing keys of our Spire server, and then we can achieve federation this way. You may well ask, can't I just achieve this using something like IRSA in EKS or managed identities in Azure? And the answer is, of course, yes, you can. However, what you're going to be doing is maintaining a lot of trust relationships that way, and you're going to have a many-to-many, almost like a web of trust situation going on, where you've got lots of different trust relationships to maintain. We think it's much better to do kind of a one-to-many thing where you've got a central point dishing out these identities. So another control that was key on the previous slide, MTLS. We had an interesting discussion before about sidecars versus eBPF. I'm afraid this talk is going to be, would you like a sidecar with your sidecar? So we are just going to throw Istio onto the cluster, because in this example, we're going to run everything on a local kind cluster and just use Istio to give us that MTLS. However, we do not want multiple issuing authorities for workload identities. If we used Istio and Spire, you can say, wouldn't we just get two forms of identity? We would get the Istio identities used for MTLS, and we would get Spire identities. We want to integrate the two. So we're going to show later, or I should say Rick is going to show in the demo how we integrate Spire with Istio. So actually you get X509s issued by Spire, and they are achieving MTLS in the Istio setup. Finally, we want to achieve layer 7 authorization. We want our workloads in the cluster to be able to only talk to the specific endpoints which we want them to. So you could just do kind of like a layer 4 network policy, but we want to go further. So we're going to introduce OPA sidecars, again, sidecar for my sidecar. And this is going to give us a really generic way of building in policy to our workload-to-workload interactions. So Spire detail, what is Spire? So the Spire architecture is a server agent architecture where we could have one or multiple Spire servers, and we have agents running on nodes which talk to these servers. We then have workloads talking to agents. So there's two key concepts to get our heads around. The first is node attestation, and this is how the agent proves itself to the server. And there's lots of different node attestation plugins. You get them for each cloud provider, you get them for Kubernetes. Because we're working in a Kubernetes cluster here, Rick's example later is going to be running on a Kind cluster, like I said, we can use projected service account tokens for this node attestation. So the agent is going to have a service account token with an audience of the Spire server and a configurable lifetime. So workload attestation then is how do we actually get our identity documents to our workloads? So workloads will be running on the same node as the Spire agent. And usually they'll talk over a local Unix domain socket so that the Spire agent will expose an API locally. It's a bit different in Kubernetes, like we say, because although if we wanted to implement this, we'd have to host mount the socket into workload pods, which isn't great from a security point of view. So what we actually do is use the spiffy CSI driver, which is a nice utility to allow workloads to talk to this workload API. Now, when it comes to how workloads get an identity, the server has to have a concept of what workloads it should be authorized to dish out identities for. And this is the concept of workload registration. We need to create a workload registration in the server, which will say, this is the spiffy ID of my workload. And these are a bunch of selectors which tell me what the workload should look like. These selectors are queried. So the agent will query something local. In the Kubernetes case, it will be the kubelet. This could be done by service account or something like that. But basically, the agent will query locally and say, oh, I know this call has come from this pod. So that's how we get workload identities for our workloads. It's worth mentioning, we've mentioned this OIDC discovery service in here. This is how we would expose our keys for the Spire server to our IAM provider in the cloud. We've also mentioned the Spire controller manager on this slide. I'll speak about that in the next slide or a couple further on. So this is a simpler box diagram about what is going on here. You can see we've got our workload talking to the Spire agent and then to the Spire server. This is the process of the workload getting its identity based on those selectors we talked about. The Spire server publishes its JWKS for signing keys for these identities it dishes out, publishes those via this OIDC discovery service. We then set up our cloud OIDC provider and point it at this discovery service and say, trust this, please. Then with an appropriate IAM role and policy, we can set up the right trust relationship to allow our workload to authenticate to a cloud service. So here we're just going to pull something from an S3 bucket. We're saying that this is going to, your workload could be running anywhere, and we could be talking to any cloud provider. So this is a really nice way to do workload authentication. Spire Istio integration details. I promised some integration here. So Istio has the concept of the Envoy secret, because obviously Istio uses Envoy proxies, again, another sidecar in every pod. if we define the Spire agent socket path, if we set this path to match a predefined socket path for the Envoy secret discovery service, what this does is it allows Envoy to pick up X509 certificates from Spire. One constraint, and yeah, we mentioned the Spiffy CSI driver before. One constraint here is that we have to use the Istio Spiffy ID pattern. The way we can get this nicely and in an automated fashion is to use the Spire controller manager, which is that box we had on the previous diagram. What this does is it watches for pods and a custom resource called a cluster Spiffy ID. So you can see here we have a cluster Spiffy ID being issued for any workload in a namespace which is labeled with example true. And it will get a Spiffy ID which looks like this. So trust domain / namespace / service account. So yeah, the Istio spec. Slightly contrived because if we have, we may want to have a naming convention which is organization, tied down to organizational function rather than specific clusters. But for the purposes of this talk, we can get workload identities this way. I mentioned OPA. Why would we introduce another tool at this point? Isn't this complicated enough? We want to show a really generic use case. Istio's authorization policy feature is powerful. However, some use cases might not be supported. We might want to make authorization decisions based on external data extracted from a database. Maybe workloads are associated with certain business functions and there's business data which drives the policy. So what we're going to use is Istio custom authorization, delegating decisions to OPA sidecars. Again, hello sidecar, my sidecar. We do this by Istio custom authorization. This is what this looks like. So starting from the top here, first of all, we inject OPA sidecars using the Caverno cluster policy. We have inbound requests to our example workload 1. These, of course, go via the Envoy proxy, which says, I have a service entry. I want to send this request, and I've got an authorization policy. I want to send this authorization request to OPA. OPA makes a decision based on some data in bundles that it pulls in. We're going to use bundles which are served in S3, and OPA is going to pull these bundles in using the exact same method we talked about before. It's going to get an SVID, an identity document from Spire. It's going to use that to authenticate to the S3 bucket and pull in its policy documents. So we've got this little thing here, which Rick will show off later, called a Jot Watcher. This is going to be yet another sidecar, which is going to retrieve an identity document and share it with the main container, with the OPA sidecar, sorry. Once all that's done, OPA returns a result and we get traffic to our workload. Worth saying that normally we would have some sort of policy pipeline up here where we can introduce security controls, which we will talk about a bit later, if there's time. This is such a big diagram when we put everything together that we've presented it as a GIF. Don't bother looking through all of it now. We'll make the slides available. The key point here is draw data flow diagrams, annotate them, threat model them with your team, and understand what can go wrong. So we'll wait for the GIF to do one rotation. We've seen the workloads talking to each other. When it goes up, we should see the workload talking to a arbitrary cloud. There we go, external workload or cloud provider API. So yes, let's not look at more diagrams that big and complex. This is going to introduce Rick's section, which he'll do in a minute. The next thing we want to do is build a prototype. We can't threat model just by using architecture diagrams. We need to understand the integration. We need to understand how things fit together in order to understand how we could break them as an attacker. So build a prototype. The goals of our prototype, we want to understand, like I said, how things integrate and what can go wrong. We want something quick and easy to spin up. So we're going to use a local kind cluster with a minimal set of AWS resources. So in a couple of weeks, we'll make the repo we're about to share public. It's still got a little bit of tweaking to do. We'll make that public, and you should be able to clone it and run this yourself. By only spinning up a few AWS resources. Most things are just running in kind. In production, we showed the OIDC discovery service before. This is how we would make available the JWKS of our Spire server. We don't want to have to serve things from a domain and set up DNS records and stuff. We're just going to host this from an S3 bucket. So we're going to publish all the OIDC information to an S3 bucket, just helping us to do this simply. We're going to show two demonstrations that Rick's demo is going to be hinged on. First of all, we're going to retrieve an S3 hosted file from a pod in our cluster. We're going to use the Go Spiffy library to do this, and Rick will talk you through the code later. Multiple community examples can help us here. So there's something called a emissary, which works with the external authorization thing we're using OPA for. Effectively, if you've got outbound traffic from a pod, a emissary will say, fetch me a JOT and inject the JOT into a header. The Spiffy helper is another project which can be used to get X509s. Worth mentioning, a few of these projects are actually in need of community help. So if you're interested in this workload identity stuff, there is lots and lots of useful stuff to be doing in the open source space. Next, so our example 2, we're going to show two workloads in our cluster. We're just going to deploy two example workloads. They're both going to be pod info, the pod info application. And we're just going to show one being able to reach one specific path, the /version path on the second, and the other one, the second, can retrieve information from the /metrics path on the first. Very simple example. Again, Rick will show you the detail. In this case, like I said, the OPA container is going to get its policy information using this JOT Watcher sidecar, which we developed. So now we finally get onto threat modeling the details. So we had a really high level threat model. We built an architecture. Now we've got to keep asking the question, what can go wrong? We have to keep doing this iteratively. I'm not going to go into all the detail here because it would take too long and we're running low on time. But what we can do is show the method. What we like to do at ControlPlane is use attack trees. And Kelly Shortridge has showed us a nice way of creating attack trees as code. If you look at the deciduous application, you'll be able to build this stuff yourself really easily. We're just going to use Graphviz under the hood, and we are going to use the following key. So green nodes are OR, blue is AND, the gray ones are just single nodes, and the red nodes are out of scope. So that's going to be all of our funky software supply chain, what can go wrongs. We build an attack tree by starting with a goal at the top. So our goal here is to leak sensitive data. And we ask ourselves, how can we do this as an attacker? We could sniff traffic in transit. We could exfiltrate data. And we keep going. We go one level more. We won't go through all of this attack tree because it will grow and grow and grow. The only thing to say is that we add iteratively. So this is the next level. And we have another level. This is even a small subset of what the true attack tree would look like for this system, because you can see we end with things like this. So compromise Spire data store. Well, you might say to me, we haven't designed how Spire is going to store its data. There's been nothing on a previous slide about that, and you'd be quite right. So this is where you would threat model the detail as the next iteration. We're just going to focus on an interesting path through the tree. So looking at this path here, leak sensitive data, exfiltrate data. We can go to this blue node here, exfiltrate data via external HTTP call from OPA container. So if the OPA containers have access to policy bundles, and those policy bundles contain data bundles, for example, OPA has the functionality to reach out via HTTP requests. Can't we just start exfiltrating stuff from there? What would I need to be able to do this? I would need to be able to compromise a policy. So if I want to do this, I need to have a deliberate policy misconfiguration and a path available to our attacker. So we've got some controls here. We talked about egress control. What about this bit here? I need to be able to access the policy repo, or, because it's a green node, I could write directly to the policy bundle storage location. Let's take an example where there is an IAM misconfiguration and someone can write to the policy bucket because something is disastrous in production, policy isn't working, please push a working bundle ASAP, the pipeline isn't working, everything's on fire. Stuff like this happens, right? And you're one misconfiguration away from that happening, one IAM misconfiguration away. So what we want to do is introduce some signing. And we're going to show a really nice control, or I should say Rick will show a really nice control where we can actually do custom signing of OPA bundles. So designing controls, again, won't go into the detail here, but what we would normally do is write our threats, and for each threat, write down our controls, as simple as that. And we want to make sure that we have full coverage and no gaps. And we always want to be designing for defense in depth. One control deep, as we said, is not the best approach to take. So looking at this bottom one here, overwrite policy bundle, this is a threat we discussed. Policy bundle signing and verification is what we're going to focus on. As we said, some controls will need further architectural work, such as the Spire data store example. The example attack path that we're looking at is just what we talked about. So how do we do policy bundle signing and verification? OPA policy signing usually requires you to provide a path to the public and private keys. However, I think we can do better than this because the OPA contrib repo shows us how to employ custom signing. We can take this one step further and implement custom signing and verification using key pairs stored in an AWS KMS, for example, a cloud provider key management system. What this means is that the signing is done within the key management system. It means that you can do automatic rotation. One thing that happens quite often is someone will set up bundle signing, say, yep, done that. The key will never change. Lots of security benefits here. And with that, it's over to my good friend Rick.
Okay, so yeah, the kind of key points around this talk is threat modeling. This is kind of threat modeling. We're going to go to the demo now. I'm going to show you some things and how they work. The threat modeling is kind of really important stuff, and also that prototyping early. So you build something, you kind of play around with it, figure out what's going on, then you keep iterating around what could go wrong, what kind of going on there. And so we're going to be making this repo available. So it allows you to kind of run these things. I'm assuming there's a fair amount of Kubernetes use in here. Hands up, who's using Kubernetes? Cool. Who's using Istio? Okay. Anybody used OPA before? Anybody used Spire before? Okay, cool. So some of this stuff might be quite interesting to you to kind of see how it works, how it's configured. And as I said, when we make the repo available, you can play with it in your own time. So let's we'll have a nice simple README file, which is great because I'm getting old and it's getting late, and I'll forget which commands I need to run. So I've got a current cluster running because you don't want to be sat there. That'll be the end of the talk. And I've preloaded a bunch of images in there, and I've built and kind of preloaded some of the little services that we've got for this talk here. So it just kind of helps things start up a little bit faster. So let's deploy Spire into our cluster. And so, yeah, James is not just frugal with his time and money, but also with yours. And so normally, if you're running a cluster, you'd have internet access. And so for the OIDC discovery thing with the JOTs, you would have a public endpoint, and you could then point your cloud provider to that public endpoint. But we haven't got time to wait for an EKS cluster to come up, and we don't want to mess about with DNS and anything like that. So James ingeniously came up with the idea of putting the discovery document and the keys into an S3 bucket, and then using that as the issuer. So as well as the kind of configuration to bring up Spire, we've got an S3 bucket to put the OIDC configuration in there. And then in AWS, we can configure an OIDC provider. So this is how we can federate from our Spire identities to our AWS IAM roles. And then, so we hand out the X509 JOT, or the JOT SVID to our workloads, and they can then talk to AWS and exchange that for temporary AWS credentials and get access to roles policies, and then services. We've got a bunch of templated configuration files here. The key thing is that we've got a trust domain here, which is so within Spire you have trust domains, and you issue identities within your trust domain, and you can federate trust domains and do all kinds of stuff. We won't go into that detail at the moment. And the Spire issue here, we'll point this to our S3 bucket, which the JOT issuer there, so that when we get our JOTs, we can hand them around, and you can get the discovery document and then the key set to verify those documents. So these are not just strong; these are cryptographically verifiable documents. And is everyone familiar with OIDC? Yeah. So in order to populate that S3 bucket, we've got to get the key set out of Spire. So we've just got a simple little helper application here, using the Spire Go libraries there. We'll create a new JWT source. Using the trust domain, we can then download the bundle, marshal it out to a file, and write that key set bucket. And to go along with that, we've templated out our discovery document. So we've got an S3 bucket there, and we're using that on all of our JOTs. From that, we can then get the URI for the key set, and then because we've got the keys, we can then retrieve the keys, and then we can verify that without having to say mess about with public clusters and DNS and stuff like that. And just the key set itself. So that's there. Let's just pop back. So we can see we've used Terraform just to create all that AWS stuff. Then we've deployed Spire stuff. We've extracted the key set. So at this point, we've now got functional Spire server, which is basically just a vending machine for identity documents. You can get X509 SVIDs, which you can use for TLS, mutual TLS, signing, all that kind of stuff. Or you can get JOT SVIDs, for example, if you wanted to traverse that's terminating the traffic, it's to go through the X509s as well. Get past the TLS there. Are you with me so far? Right, I forgot what I was going to do next, so I'll go back to my README file. So, yes, example one. Yes, we're going to consume something from S3. So we're going to deploy an application, view the logs, and just see what it got from S3. And again, there's a bunch of Terraform stuff. So while that's running, we'll pop back and see what's going on. So target bucket, just an S3 bucket, and policy document that allows us to access that bucket. File we're going to load into that bucket. And we've got federated role. So this role is attaching that bucket access policy and switching into the OIDC provider that we just previously configured. It's not quite easy to see what's going on here, but we're basically, if the audience for the issue of that JOT matches the audience that we configured here, that's partially there. And then if the subject in that JOT, the subject claim in that JOT matches the awful spiffy format of no, it's not spiffy, but the awful Istio format that bleeds implementation details of your workload identity all over the place. That says that in the default namespace, service account with the configured name, then you can access then you can access that bucket. And then we've got a simple consumer application. Now this is doing it the hard way. So we're getting our token, our .SPID, and we're exchanging that for temporary AWS. Anybody using or use IRSA or Web Identity Federation with AWS? That's super cool. Basically, you got a job that's got an OIDC provider, and you put the correct set the correct environment variables, and the AWS CLI or however you access an AWS, you will just use the default credential provider, and it will do this hard work for you. It will swap your job for temporary credentials without you having to worry about it. But I've done it the hard way here just to show you what's actually going on under the covers. So we get those credentials, load the file from the bucket, and just write it out the logs. And, let's have a look and see if we can see that file. James, can you guys see it? It's quite small. James is a big fan of certain pop star. So that was the simple use case. So our workload is it's got a sidecar that reads the job, writes to the file system, and then we exchange that for AWS credentials, and that allows us to access the S3 bucket. You might say to yourself, well, with IRSA, we can just do that. We can configure our Kubernetes cluster to just talk to AWS and do all of this without worrying about this. Well, that's fine if you've just got one Kubernetes cluster. But if you've got 2 or 3 or 4 or 5 or 500, you've got to configure that OIDC provider for every single cluster. If you use a centralized identity provider, you only have to configure that trust relationship between your cloud provider and your identity provider once. So it does simplify things there. Everyone happy with that? So far? Right, now we're going into sidecar hell. So also James Smith has talked to KubeCon. So it's great from a security perspective, but he also really wanted to get in there. So what he basically did was he sat down and looked through the CNCF's list of products. The more of these we can get in there, the more likely we are to get accepted. So we've got Spiffy Spire, we've got Caverno, we've got Istio, we've got OPA, we've got Kubernetes. We're well in there with products. So let's deploy Caverno and Istio, and then while that's running, we'll talk about some of the stuff that's going on. So as James mentioned, we're using OPA bundles to define the policy rules for our Istio authorization. So we need a bucket to put the bundles in, and then we need a policy that allows you to read from that bucket. To go with that, we're also going to sign those bundles, because if you can put that, we want to make it more hard for people to mess with this stuff, right? So you've got to have permission to load it in there, got access to the keys. The other benefit of using the keys in AWS KMS than the kind of standard off the shelf open signing is you have to kind of pass the keys around. So your pipeline needs access to the key to sign. The workloads that are downloading the bundles need access to the public key to verify those signatures. And as you start moving these around all over the place, that kind of management becomes a bit of a pain. So as we went through that second level of threat modeling, we've added additional controls. And so we've implemented custom signing using AWS KMS keys. So the keys stay on the cloud provider. We can get the public key if we need it to verify things, but that private key never leaves the cloud provider. So more difficult for people to mess about with our bundles and put dodgy policies in there. And then we've got a role. So we're attaching the bucket access policy there and KMS verifier policy to our OPA role. And again, we're using that spiffy ID to authenticate to AWS. And as long as we are workload 1 or workload 2, then we will be able to download the bundle and access that public key to verify. We've got some template configuration files in there. The interesting stuff is our OCA policy. So by default, you can't do that. But if you are workload 2 and you're trying to talk to workload 1 on the version path, you can do that. If you are workload 1 and you're trying to talk to workload 2 on the metrics path, you can do this. This is just simply using the pod info. So these paths are just available. So it's not a real thing, but you can see how the policies work. And then we've got a Job Watcher sidecar. And so it's similar to the one that got the JWKS for us before. We are creating a source, figuring out where we want to write the token, get the token. And this one is periodically refreshing it, because while I'm waffling on, this token could be expiring because they're very short-lived. The demo won't work. So James put a little loop in here, and it's periodically refreshing it. So by the time we get around to it, it should all be good. And so back to the demo. Let's just have a little look. Okay, so what did we do last? We deployed. So now we're going to sign and publish our bundle and deploy those 2 workloads that we were just talking about. One application, 1, 2, 3, so. There we're running, which is a bonus. Go back to the old man's cheat guide. Yes. So we're just gonna because so Istio will generally act as its own PKI and vend its own X509 certificates, but then we've got one workload with multiple identities. So we've swapped Spire in there to hand out the same identity, whether it's an X509 or a JOT. It's going to have that same spiffy ID in there. So before we try and do the interesting stuff, let's make sure that works. And yes, Istio is vending ControlPlane certs. We're not out of the woods yet, but it's looking positive. So we're going to send some requests backwards and forwards and make sure that Istio is checking with OPA to see whether these things are allowed to talk to each other. And with this, we can see that workload 2 was denied talking to metrics on workload 1, but allowed to talk to version on workload 1. And workload 1 was denied talking to version on workload 2, and was allowed to talk to metrics on workload 2. And a little bit of luck, that was what our policy said we could do. And that's the end of the demo. It's, as I say, the star of the show is James. Threat modeling and prototyping was the message. This repo allows you to kind of play around with some of these tools. So we can talk about some other stuff on a different time. But we've implemented our custom controls. We've done some identity switching, switcheroonies. We've talked to S3. We've talked to workloads when they're allowed. We haven't talked when they're not allowed. And we've implemented custom signing of those open bundles with the keys always staying nice and secure. You know, very much. In what respect? In doing all of this stuff under the covers. Yeah. So they're not calling these sidecars all the time. The sidecars are sitting there, just kind of helping you out. So the Jot Watcher is just kind of periodically checking with Spire to see whether the Jot has expired. So it's kind of the Jot expire. So it's doing that. It's right to the file. So that's just kind of sitting there doing that. Inspire the workload API will proactively go and get X509 certificates and cache them. They tend to have a longer lifetime, kind of valid for sort of 24 hours. You can configure this, but by default they're valid for 24 hours. And so the agents will actively go and get those refresh them so that they're there. So this is kind of preemptively occurring. With Jots, it's slightly more difficult because you tend to get them on demand. So it's I'm about to call this service, so give me a Jot to allow me to call this. So there is a small hit there because of the audience in there. So your workload is going to talk to the agent, but it's talking through a unique socket. But the agent will have to talk to the Spire server in order to send that Jot and send it back. With OPA, the OPA sidecar is talking to in this case AWS S3 to download, verify that one periodically. So the kind of bundles there. So when the requests come in, the OPA sidecar is making that call locally to OPA. So it's not hitting. So there is, depending on which bit of it you're talking about, it in which period of time, there will be a little impact there. But a lot of this stuff is kind of optimizing and doing stuff in advance where it can.
By the onboard proxy to external authorization services. I think that you're right. There will be some latency added. The question is, what's the security? It's not just the security, right? It's coupling policy from the application. Otherwise, you have to make policy So there are other benefits other than security, but that decoupling outweighs the potential added. So it's a balance. As with everything, when we say that model, it's all about it's some right.
Woo! Sorry, I got lost in the Ric Flair and forgot the question. Did you?
I got the question. Yeah, it's a good question, Lewis. Thank you for the Ric Flair reference. The answer is we would have to threat model it. That's the message of this talk, right? We would have to threat model those denial of service opportunities. So Lewis, you're right. If you can compromise the spy server, one of the attack trees that we didn't draw, but which we should have done, is compromise the attack server, make it impossible for it to serve SVIDs. Yes, absolutely. If all your old SVIDs have expired and you can stop new ones from being minted, then yeah, you're pretty you're screwed. Yes, high availability would have to be factored into the design of anything which uses something like this, which is why doing this in production, that would have to be such a main consideration of your architecture, the high availability of it. But yeah, good point. Yeah, exactly.
So yeah, there are many benefits from making the platform provide these kind of services to your application developers. Of course, once we bought Liz's book and figured out how to do eBPF, we can come back next time and show you how to do this without all of these sidecars. We cannot do that. So sidecars are us. Yeah, thanks. Thank you for having us.